Hey, what's poppin', my eventual victims of climate change? Today, we're going to talk about Hooke's Law. This is not necessarily a two-dimensional um, unit it's not necessarily a two-dimensional thing. I probably could have taught this last unit, but we'll slip it in here just because we need to talk about this specific law because it's very, very important. And we haven't talked about it yet. So, you got to learn it, and maybe if I don't know, I don't have a joke for this, but we're gonna learn Hooke's law, so that's why. All right, so let's talk about what Hooke's law is. Hooke's law is going to help us calculate forces for springs. Disclaimer, I haven't checked. I probably should have before I started recording, but if you see the word string, I probably meant spring throughout this entire lecture, so just bear with me. I'll point out if we get there, but hopefully you don't notice. So, we're going to talk about springs because springs, hopefully, most of them will obey this thing called Hooke's law. And it's actually a very simple law. It's not like Newton's laws where you have to like really think about it and you get these weird like sigma equations where you're like, that's not a sigma. Sigma equations where you're adding forces together and looking at x's and sum of forces and y's. We'll incorporate this later, but for right now, we're just going to worry about how do I figure out how hard a spring pushes or pulls. So let's go ahead and talk about what Hooke's law is. So Hooke's law is used to determine the force necessary to either compress a spring or to stretch a spring, right? So springs, right? Let's say here's like a wall and you've got a spring you wedged up against that thing. Springs can go one of two ways. You can either take your hand and push this way and then get a spring that's more tightly coiled, like that. Or you could put your fingers right here, grab that thing, and then pull on it. And then you could stretch it way out like this, right? So springs can go two directions, in or out. And then most springs have a position where they're happy to just chill at. We're going to call this the equilibrium position. Equilibrium, sound it out. Position, meaning it's like at a happy resting state. This is where it just wants to chill at, right? It's vibing. So we have this thing called Hooke's law that will tell us how hard we have to push to get to squish this much, or how hard we have to pull on it to get it to extend this much. Hooke's law is the force required to either compress the spring or stretch the spring is equal to negative kx. So let's talk about what all these things mean. Like most signs in physics, because force is a vector, this thing is telling us a direction. This negative sign is just for direction. K is what's called the spring constant. And this is, we'll talk about that more on the next slide or two. And then X is what this direction is. We might actually want to call this maybe delta X. It's how far you are stretching or compressing. Okay. So let me maybe rearrange this a little bit and show us maybe a more intuitive way to think about Hooke's law. This is how you will generally see it in physics textbooks, on equation sheets, things of that nature. I think it might be a little bit more intuitive to think about it like this, K times negative delta X. So this negative is purely due to direction of compression or extension. And let me show you an example with this stretch spring here. If here is our equilibrium position and I stretch to the right, let's say to the right is positive just like normal. So I've pulled this spring way out here. What direction is that spring going to pull on you when you pull that spring out? The spring is going to pull that way and try and get back to its equilibrium position. So this direction of delta x is in the opposite direction of the force of the spring, because spring forces are restorative forces. When you pull or push a spring out of position, it tries to restore itself to its happy equilibrium position. So whatever you do, the spring does the opposite of that, trying to go back to the way it wants to be. So this negative is in the opposite direction of our displacement or our stretch or compression. So this is just saying, take whatever direction you stretch or squish your spring, reverse it, and that's the direction your spring force will be pulling or pushing. Okay. Let's go ahead and talk about K. So if we ask ourselves, what is K? K is, in Hooke's law, it's known as the spring constant. It is a constant value. It doesn't change for your spring. And it's a measure of how stiff your spring is. Big K equals very stiff. Small k equals squishy. Okay, so if you think about, let's see, what's a spring you might be familiar with? Like a spring in like your Xbox controller or your PlayStation controller on your like trigger buttons. You can pull those in and push them with just your fingers, right? Like if we're thinking, we've got our remote here. What do remotes look like? They've got like a little joystick thing, right? And then they've got like, anyway, a remote, right? And then over here, you've got like your trigger. If you pull this thing with your finger, that thing's super easy to compress. So this would have a very small spring constant. Another type of spring that we could think about would be something like in your car. What do cars look like? Something like this. This wheel has a suspension on it, and inside there you can see springs. The back actually probably has a leaf spring, which is more like that, but the front usually has like a coil spring. If you ever took one of these out of your car and then you like stood on it, it would squish, like you have your spring and then it would squish a little bit, right? But these things are incredibly stiff. They're big, hardy springs for cars. This thing is going to be a lot harder for you to compress than this thing. So it would have a much larger K value, whereas this would have a little bitty baby K. All right. So that's what the spring constant is. It's unique to each spring. And there's not a way that you can look at a spring, observe it, go, that one looks shinier than the others I've seen. I bet its spring constant is 12, right? You can't look at a spring and just tell. You have to experimentally measure it to figure out what it is. Okay. Let's talk a little bit about the units of everything in Hooke's law. So let me clean this up. So force is force, right? Force is always measured in newtons. X is a displacement, or how far we're traveling. That will be measured in meters. And then we have K. So let's figure out what the units for K are. Pardon my grammar there. If we replace F and X with their units, and then we solve for K, that'll tell us the units of K. Divide by meters. So K is going to be measured in newtons per meter. The way you want to think about this is I have some spring like this, and I want to compress it 1 meter. How many newtons of force will that take? Well, if it takes 500 newtons to do that, then our spring constant, K, would be 500 newtons per 1 meter. Whoops, not one, sorry. Per meter of displacement. And that's in either direction, stretching or compressing. So this number is telling us how many newtons do I have to apply to get 1 meter of motion out of my spring. And this is not necessarily implying that our spring can be compressed 1 meter. If you have your Xbox controller or your PlayStation controller, you know that trigger doesn't go a meter in either direction, right? It goes like a centimeter, right? So we still use the same units. Sometimes you might even see this in like 500 newtons per centimeter. Same idea here. It's amount of force per amount of stretch that you want. So there we go. Okay. All right. So that's Hooke's law. That's K. That's X. That's our force. We talked about all of that. We talked about the direction. All right. Let's answer some important questions that might come up on your AP Physics test. Or actually, I'm sorry. Let's talk about assumptions first. Then we'll talk about important things on your AP test. So, like most of physics class, we can't do a lot of actual real life stuff. Part of that is because actual real life stuff is incredibly complicated. The second reason is the math is incredibly difficult. And the third thing is you're in high school and we've got to shelter and protect you from any dangerous ideas like, a sustainable living wage and healthcare for all. So what we're going to do is we're going to make some assumptions that we know are not true about springs in real life, but they're think of them like rounding ways that we can approximate real springs to make our calculations a little simpler and to avoid a lot of the needless, well, I need to know this number, well, I need to know this number, and I have to measure this, and you have to tell me this. It just simplifies the problem so we don't get bogged down in all the specific nitty-gritty computational stuff. Okay. So the first assumption we're going to make is that springs are massless. So if I have like a ceiling and I've got a spring and I hang something from the spring, the weight of gravity will pull the mass down. But in real life, if you have a heavy spring, the spring's own weight will make the spring extend. If you have a heavy spring that has whatever this, it's all connected, that has this resting length or equilibrium length, if you just hang that thing or hold it by one end and let it dangle, a lot of times that spring will stretch out a tiny bit because of its own weight. So we just ignore the weight of the spring. They're like strings in this class. We assume they're super lightweight, made out of some fancy space age carbon nano material stuff, and ignore it unless they tell us otherwise. Okay? We also assume that springs can stretch forever, which is objectively not true. If we take a spring, all right, here's our spring, and you stretch it, it's going to progressively get skinnier and skinnier until you stretch it all the way out and it's just a flat cable of metal, right? You can stretch a spring so far it turns into a wire. And then when you let go of this thing, this stretched out spring that started like this will probably go back to looking like that. And it'll be all stretched out and messed up and you'll never be able to use it again. So we ignore that idea and we say, you know what? You can just stretch that thing as far as you want. It'll stretch forever. Okay. This is just to avoid, well, how many coils are in the spring? How much total material is the spring made of? Can my spring even stretch 3 meters? That doesn't seem realistic. I've never seen a slinky that long, right? So it avoids all that like needless, weird stuff that we don't want to think about. Likewise, we can squish them forever. Normally if you take a spring and you squish it so that it's like this and all the coils are touching, it just won't squish anymore because it gets in its own way. We're going to just assume you can compress that thing as much as you want. We think of our spring as being way stretched out, and this distance will be super far from this distance so that we don't worry about our spring running into itself. It's very thin. That's how we got it to be massless. The last thing we're going to assume is that our value of K does not change when we stretch or compress a spring. Like I mentioned, if you have a spring like this and you stretch it out to a wire, when you let go of it, this thing is going to be like permanently stretched like that. And that damages the spring and in real life changes our K value. But like K itself, the amount of damage you do to the spring can only be experimentally measured. It has a lot to do with what metals our spring is made out of. It has to do with how it's heat treated to be turned into a spring. There's a bunch of very specific things for specific materials that have to be experimentally verified. And we're not about that life. This is more of a theory class than a practicality class. So we're going to assume these things unless they tell us not to. All right, so let's start doing some spring problems. This is a problem that I have seen come up on the free response of AP Physics tests a lot of times. They give you some spring and they say, go ahead and tell us what K is for your spring. So let's talk about if I give you some random spring. I just hand you this little springy piece of metal and I say, what's K for that thing? How are we going to find that? Let's talk about how we could set up an experiment to verify that. So to start our experiment, we've got our spring, and all we know about springs right now is Hooke's law, F equals negative kx. All right, what we are looking for here is K. So the way that you in this class will try and set up any experiment, your goal is to graph two variables and get a straight line graph. And then hopefully either the slope or the area is the interesting thing that you've been asked to experimentally measure. So if we look at Hooke's law as a general equation, we could say this is, oops, I've got stuff in the way now. Ooh, let's move all this stuff over. Okay. And let's change colors so that this looks a little, actually, where's my pink? Let's get pink. Okay. We could look at this as y equals mx plus b. B in this case is 0 because this is what's called a directly proportional equation, meaning it's linear. So our x is to the first power and its y-intercept is 0. So because Hooke's law is a directly proportional equation, all we have to do is make our spring the slope, our spring constant the slope of our graph. So what we want to do is measure the distance that our spring is stretched and how much force it takes to stretch that. We make our force the y-axis of our graph, our displacement, our x-axis of the graph, and then our slope will be K. We're pretty much going to ignore this, this negative, just knowing that springs pull the opposite direction they're stretched. But if we have a spring and then we hook this thing up to a force gauge and then we stretch it, and this thing says 18 apparently newtons, and our spring has stretched this far, we'll call that 4 centimeters, then both of these seem positive, And we're not really going to worry about it. We know that this is purely directional, and we have the good conscience to throw it where it needs to be, especially when we're doing force diagrams. So don't worry about too much. We'll just look at the slope of this to find k. All right, so that's how we could set up our experiment. We could measure the distance it travels, we could measure the force, and then the slope of this would be k. And you're going to say, Mr. Barton, hold on, why do I care about the slope? So every year there are, of course, students who say, Mr. Barton, why don't I just take a spring, I stretch it some known value x, I measure the force, and I throw into Hooke's law, right? If I know the force and I know x, can't I just plug in these numbers? Let's say, all right, here's 18, k, this is 0.04, just divide by 0.04, divide by 0.04, and then throw that in our calculator, 18 divided by 0.04, and we get k equals 450 newtons per meter. Why do I have to find a slope when I can just plug it in, do one measurement, and get a value? The reason for this is because real life is kind of wonky, and if you are measuring something in real life, you don't want to have a sample size of, size is a z, isn't it? Not a v. A sample size equal to 1, because let me give you a good example to maybe help you understand why this is, well, this is probably a good value, why it might not be the best value. If I am going to have a party for you guys at the end of the school year, and by party, I mean we all show up to WebEx and I mail 1 slice of pizza and 6 ounces of Dr. Pepper to all of you to enjoy at the same time. And I say, all right, what kind of pizza do you want? And I ask one student, and they say pineapple. Is the entire class going to be happy with that decision? Is that one data point that I collected reliable enough for me to say, all right, let's order 3 pineapple pizzas? I measured it, didn't I? Isn't that true of the system as a whole? Well, maybe I did my measurement wrong. Maybe I asked that weird kid that Naruto runs to lunch, or whose starter Pokemon was Bulbasaur, right? Maybe I got one bad data point somehow, and it's not good. So when we collect multiple displacements and multiple forces, graph them, and then find a trend line, and then look at the slope of that trend line, that is just a much more reliable way to measure something, because we have more data to either tell us we're right, or what would be really weird is maybe we don't even have a spring that follows Hooke's law. Maybe it stretches easier the farther it stretches, and we find that our data points, our data points do this, and it's not even linear, and it curves up. That's something we would want to know by doing an experiment. So that's why we want to take multiple measurements and look at a slope. So to measure k, we measure displacements, we measure the amount of force required to get that much displacement, we graph force on the y-axis, displacement on the x-axis, and then our slope here, our slope tells us k. So here I have exactly that. I've got some data. Here's my data table. Here's my displacement, and I did no displacement. So this is just my spring sitting there with a force gauge attached. Oh, look, my force gauge doesn't even say 0. Isn't that crazy? So you can tell in real life you got some error. This is 10 centimeters, 20 centimeters, 30 centimeters, 40, and so on. And here's all my force gauge readouts. If I graph them, you can see they wiggle a little bit, but they follow a general trend. We get the equation of this trend line, and I've already got it right here. So we've got a couple of things here. Right? We have our slope, which we've already talked about. This slope should be our k value, and this y-intercept is, what is that? This is f equals just kx. We're dropping the negative just because of the way we measured things, and we know it's a direction. We're not too worried about it. Plus b, what is that y-intercept? So this would be our k value. If we took these measurements, recorded these forces, we could pretty confidently say k equals 24.838 newtons per meter. And then this y-intercept is just error. Because of Hooke's law, we know that there isn't a y-intercept, and it should be equal to 0. But because force gauges are a little sensitive, and maybe we didn't pull it exactly 20 centimeters, maybe we pulled it 21 centimeters, and we measured this value. Just because our school rulers have been chewed on by a bunch of dumb physics students from the past, things like that, it's just hard to measure and get reliable data. So we look at it, we compare our results to our theoretical equation, and we say, oh, you know what? It's a very small number. Look how close to 0 that y-intercept is. We could throw it away and confidently say that this is error because springs that follow Hooke's law shouldn't have any force to stretch it no meters, right? That's what this would mean. This would mean I would need 0.6942 newtons of force to stretch a spring 0 meters. Just by it existing, this much force has to be there. Otherwise, God knows what happens. Okay, so that's an example of how we could set up that experiment. I just want to make sure that we're comfortable with how we would experimentally measure K, because I've seen this exact question show up on the AP test before. All right, so now let's do some example problems, and then we'll get you on your way and you can go practice your own physics. So a spring is held stationary at one end and is stretched a distance of 0.5 meters. It takes 8 newtons of force according to a force gauge pulling the free end of the spring. What is the spring constant of the spring? Well, Mr. Barton, you just said that we need more. Listen, we're doing an example problem. We're just solving for something. Don't trip. This isn't like a life or death scenario to make sure that our Xbox controller is optimally springy, right? This is just a physics problem just to make sure we can do math. So we look at our spring, and then it's stretched from here to here. We get X equals 0.5 meters. Half a meter, that's pretty far. That's like 1.5 feet. And it took us 8 newtons of force to do that. Okay. This means, because of Newton's third law, that if I apply 8 newtons of force to the spring applies 8 newtons of force back on me. Just so we're clear, just so we make that connection. So if we look at Hooke's law, F equals negative kx. We're going to assume that to the right is positive. Okay. Our force is, the force of the spring would be negative 8 newtons, because if the right is positive and we're moving to the right 0.5 meter, the spring is going to pull back just as hard as we pull on it. Equals negative k times x of 0.5. So we divide both sides by 0.5. These cancel. Dividing by 0.5 is the same thing as multiplying by 2. So this will be negative 16 equals negative k. And then the negatives cancel. And k equals 16 newtons per meter. A lot of times, people will just ignore this negative. I think even on your AP reference sheet, if you go look at that appendix that I posted, I think that your spring force is equal to K times the absolute value of X, because they don't even want you to worry about the negative, because really it's just directional, and we know which way the force will pull, right? What we're really interested in is how strong is that force, and we'll say, okay, it's pulling that way. I know that's negative, right? I don't need the equation to tell me that. So a lot of times people will just drop this negative and say F equals KX, and then I'll figure out the direction at the end of the problem when I'm ready for it. Okay. All right, so there's K. Not too bad. Just find your numbers, plug them in. Let's look at a couple of more examples. So it says a mass of 8 kilograms is hanging from a spring. If the spring stretches 40 centimeters, what is the spring constant of the spring? Okay, so we've got a hanging spring, and we have a mass of 8 kilograms here. All right, we know that this spring has stretched 40 centimeters, which is 0.4 meters. And we want to know the spring constant. So we're going to have to do a little bit of examining forces and force diagrams to solve this. So let's draw a force diagram for this box. If it's just hanging there motionless, of course it has weight down, which equals the mass times the gravity. And then the thing suspending our mass, holding it up, is of course our force of the spring. And our spring force is KX. Ignoring the direction, we'll figure it out. Up is positive probably, but oh well. If it's just hanging there, we know these are equal. So we can do a sum of forces in the y direction. Let's say up is positive because I'm right-handed and that's just the way I like it. This equals the force of the spring minus the weight equals 0 because of Newton's first law. And if the forces are balanced, the sum of forces must equal 0 and cancel. Now we substitute in our equations and we make sure we use our negatives from this formula and not so much worry about the values. So this is K times our stretch length minus the mass of the box times G equals 0. Now we can go ahead and plug in some numbers and solve. So K is what we're looking for. It stays a variable. X is 0.4 minus our mass is 8. G is 10 on Earth equals 0. So we have negative 80. 0.4 K minus 80 equals 0. We add the 80 over. 0.4 K equals 80. And we divide by 0.4. And we get... Oh, that's not right. Hold on. I'm sorry. I mistyped it. K equals 200 newtons per meter. K will always be positive. Oops, positive has a P, not a B, huh? And that's just like a fact of life. It kind of makes sense just because if you think about what would it mean to need to apply negative 60 newtons if I wanted to stretch something 4 meters, I apply it in the opposite. Don't worry about it. K, we just define as always being positive, and we'll work out the directions later. All right, so that one's not too bad. This is how we would look at a force problem involving springs. We still draw a force diagram. We still do a sum of forces equation. We set up our equations, we plug in our numbers, and then we do a little bit of algebra to solve for the numbers we want. All right, pretty fun. Let's do one more. A mechanic is working on a car and decides to stand on the suspension coil of a car. That's code for a spring. This is that spring in your car that we talked about earlier. Of a car she's working on. And while it has it out of the car. So she took the coil out and she's working on it. The mechanic has a mass of 75 kilograms. If the suspension coil is rated at 5,000 newtons per meter, how far will the coil compress when she stands on it? So what we've got here is a coil, and then our mechanic hold on. Our mechanic's getting a little out of hand here. Stands on it. And we want to know what will be the compression of our spring because of this mass that's been added to it. So what we're going to do is we're going to draw a force diagram for this person and then compare. So for our person, we still have the weight of the person down, which is equal to the person's mass times her gravity. And then the spring, because we're compressing it, it's going to push towards going back to its relaxed length. So it's going to push up. The force of spring. We'll still say up is positive because that's the way I like it. And we'll do a sum of forces in the y direction once again. So now we have the force of our spring minus the weight. Equals 0 still. Substitute in our equations. So we have kx minus mg equals 0. Now we have the spring constant and we're looking for this displacement, but same process. We've done all the physics. Now we're just plugging in numbers and doing algebra. So K is 5,000 times the unknown distance minus 75 times 10 equals 0. 5,000 times x minus 750 equals 0. Add the 750 over. 5,000x equals 750. Divide by 5,000. 750 divided by 5,000. And we get x equals 0.15 meters. We know that this is in meters because the units of K are in Newton meters. If they said Newton centimeters or Newton kilometers, that would be a huge spring. Then this would be in whatever units the spring constant is given to us in. All right, so there we go. There's a couple of spring problems, a discussion about how we could do a lab to solve for them, and kind of an understanding of all the different pieces of Hooke's law. So hopefully this lesson was a lot easier and maybe a good break for you folks compared to those other multi-dimensional vector decomposition problems that we've been doing. So hopefully it doesn't ruin your day. Yeah. Cool. If you need help, make sure you tell me in the WebEx or put it in the comments below. Maybe give it a little like, a little subscribe, tickle that bell icon for notifications when I post new videos every day, usually around 7 or 8 o'clock at night. But you guys already found that out, but cool. All right. Have a great day, folks. I'll see you next time.